How does a particle travel through space? It sounds like a strange question, almost a silly one. Of course it travels through space. Everything does. You throw a rock, it moves through the air. A spaceship moves through the vacuum. An electron flies from here to there. End of story, right? But pause for a moment. What do you actually mean by travel? You imagine a tiny dot, a particle, starting here and then later being over there. You imagine it tracing a path, like a miniature bullet flying through empty space. That picture feels obvious. It feels unavoidable. But that picture is already wrong, because when you look closely, really closely, at how nature actually works, you discover something unsettling. A particle does not move through space the way you think it does. In fact, the very idea of a particle having a well-defined path turns out to be an illusion created by your brain, not a fact about reality. Let's start simple. Imagine empty space. No air, no dust, no light. Just space. Now place a single particle in it. An electron, for example. Tiny, point-like, no size you could ever measure. Now ask the obvious question, how does it get from one place to another? You want to say it moves. It has a position at one moment, a slightly different position a moment later, and so on, like a smooth line drawn through space. That's the picture your intuition gives you. But here's the problem. That picture only works if the particle always has a position. And nature does not agree to that rule. In classical physics, a particle has a position and a velocity at every instant. You can imagine freezing time and pointing to exactly where it is and how fast it's moving. That picture works beautifully for baseballs and planets. It even works surprisingly well for dust grains and molecules. But when you shrink things down far enough, the rules break. An electron does not behave like a tiny ball. It does not politely sit at a point in space waiting for you to look at it. In fact, if you insist on asking, where exactly is it right now? Nature answers with something deeply unsatisfying. It doesn't have a single location. Instead, it gives you a spread, a cloud, a set of possibilities. This isn't because we're ignorant. It's not because our instruments are crude. It's because the electron itself is not localized in the way you expect. Its position is not a fact until something happens that forces it to be. So when you say a particle travels through space, you're already smuggling in an assumption that the particle exists at places along the way. But that assumption is precisely what fails. Think about this. If a particle doesn't have a definite position, what does it mean to say it moved? Here's where Feynman's way of thinking becomes essential. Instead of asking, what path does the particle take? You ask a much stranger question. What does the particle do? And the answer is astonishing. A particle doesn't take one path through space. It takes every possible path, not metaphorically, not approximately, literally. From point A to point B, the particle explores all conceivable routes. Straight lines, curved lines, loops, wild zigzags, paths that go forward, backward, around and back again. Even paths that seem absurd. Even paths that look like they waste time. All of them contribute. This sounds insane until you realize that the particle is not choosing a path the way a human would. It is not deciding. It is not traveling in time the way an object does in your imagination. What actually exists is a process. A mathematical summation of possibilities. Each possible path contributes a little piece to the final outcome, and those pieces interfere with one another. Some reinforce, some cancel. Most cancel out almost perfectly. The only paths that survive are the ones where nearby possibilities line up instead of destroying each other. Those paths create a strong signal. Everything else fades into nothing. When you finally observe the particle, when you force nature to give you an answer, you see a result that looks like a single trajectory. But that trajectory is not a story of motion. It's the leftover trace of a massive cancellation of alternatives. In other words, the particle didn't follow the path you see. The path you see is what remains after all other possibilities annihilated one another. This is why particles often appear to move in straight lines. Not because they prefer straight lines, but because straight-line paths are the ones where nearby alternatives don't fight each other. They add up instead of canceling out. Now here's the part that should make you uneasy. If a particle explores all possible paths, including wildly indirect ones, what is it doing in between observations? The honest answer is nothing that fits your everyday concepts. Between interactions, the particle is not a thing moving through space. It is a set of potentialities evolving according to precise mathematical rules. Space, in that sense, is not a stage the particle travels across. It's a bookkeeping system for possibilities. This is why asking, "Where is the particle right now?" is often the wrong question. The particle is not somewhere in the way a pebble is somewhere. It is distributed across space as a probability structure. When you don't look, nature does not commit. And the moment you do look, when the particle interacts with something, when it leaves a mark, when it transfers energy, then suddenly you get a definite outcome. A click in a detector, a spot on a screen, a flash of light. That moment is not the end of a journey. It's the end of a calculation. Now think about how radically this changes your picture of space. Space is no longer a passive container that particles drift through. It's an active participant in how probabilities evolve. The geometry of space influences which paths cancel and which survive. Distance, time, and motion are not primary. They emerge from deeper rules about interference. This is why particles can do things that feel impossible. They can tunnel through barriers. They can interfere with themselves. They can behave like waves in one experiment and points in another. They are not switching personalities. They are obeying a single underlying rule that your intuition was never built to handle. And now comes the question you should be asking. If particles don't really move through space the way we imagine, why does the world look so solid, so continuous, so ordinary? Why don't you walk through walls? Why don't you blur across the room as a cloud of probabilities? The answer lies not in the particles themselves, but in numbers. Enormous numbers. You are made of an astronomical number of particles, all interacting constantly, all exchanging information with the environment. Every interaction collapses possibilities, over and over, billions of times per second. The delicate quantum effects wash out. What remains is the stable, classical world you recognize. But underneath it, hidden by scale and noise, the same strange rules are still operating. You are not exempt from them. You are, in a very real sense, a coordinated swarm of quantum events that has learned how to behave predictably. And that should make you wonder something even deeper. If motion through space is not fundamental, if particles don't actually travel the way we think, then what is space really? If space is not a simple stage where particles march from one location to another, then the next question almost asks itself, what is space doing while all of this is happening? Because clearly it isn't nothing. Think again about the idea that a particle explores all possible paths. Those paths are not floating in some abstract mathematical void. They are paths through space and time. The structure of space determines how those paths behave, how they interfere, which ones cancel out, and which ones survive. So space is not passive. Space is active. Now imagine that you try to follow a single particle very carefully. You set up detectors. You watch for interactions. Each time the particle interacts, you get a definite event. A click, a flash, a dot on a screen. Between those events, you want to say the particle was traveling. But traveling how? Through what? Here's the uncomfortable truth. Between interactions, the particle is not a little object moving through space. It is a mathematical object evolving in time. What evolves is not position, but probability amplitudes. Those amplitudes spread, interfere, twist, and combine according to precise rules. The motion you think you see is an emergent story you tell after the fact. This becomes especially clear in experiments where particles behave in ways no traveling object possibly could. Take a particle fired toward a barrier with two openings. You expect it to choose one hole or the other. A classical object must. But when you don't check which hole it goes through, something extraordinary happens. The final pattern on the screen depends on both holes, even though each particle arrives as a single, localized dot. How could a single particle be influenced by a hole it did not pass through? The only consistent answer is that it did not pass through just one hole. The particle's evolution involved both possibilities. The space around both holes mattered. The geometry shaped the interference. The result emerged from the whole configuration, not from a single path. Again, the particle was not deciding. It was obeying the rules. This forces you to abandon another deeply ingrained idea, that a particle's history exists independently of how you measure it. In reality, the history you assign to a particle is reconstructed from the measurement outcomes you observe. The path is not something that happened, it is something you infer. Now let's take this even further. If particles don't move through space as little travelers, then what does motion actually mean? Motion, at the deepest level, is not an object changing position. It is a change in the structure of probabilities over time. What you perceive as movement is the shifting pattern of where interactions are likely to occur next. In other words, motion is not about where something is. It's about where something can happen. This sounds abstract, but it has very concrete consequences. For example, consider a particle that appears to be at rest. In classical terms, it sits still, but in quantum terms, a particle that is perfectly localized cannot be at rest. The more you confine it to a precise location, the more wildly its momentum must fluctuate. Even in its lowest energy state, it seethes with activity. So, not moving does not mean what you think it means. Even empty space is not empty. Even when there are no particles, the fields that define what particles could do are still there, fluctuating, vibrating, restless. Space itself has structure, it has energy, it has rules. And particles are not separate from that structure, they are expressions of it. This is why modern physics increasingly treats particles not as fundamental objects, but as excitations of underlying fields. An electron is not a tiny bead traveling through space. It is a ripple in an electron field that exists everywhere. When the ripple moves, what is moving is not a thing, but a pattern. Now ask yourself something unsettling. If particles are patterns in fields, and fields fill all of space, then what does it mean to say a particle is here rather than there? It means that the pattern is more intense here than there. It means the probability of interaction is higher here than elsewhere. That's all. There is no sharp boundary where the particle suddenly stops existing. There is only a continuous distribution of influence. And when that pattern changes over time, you call it motion. This also explains something that once seemed paradoxical. Why particles can appear to be in two places at once, or why they can affect outcomes without following a continuous path between cause and effect. They are not sneaking around behind your back. They are not cheating. They are obeying rules that do not respect your everyday categories. Your intuition was trained on large objects made of many particles interacting constantly with their surroundings. In that regime, probabilities collapse so rapidly as so thoroughly that motion looks classical. Paths appear well-defined. Objects seem to occupy definite locations. But this is a special case, not the rule. Now let's bring time into the picture. So far, we've talked about particles exploring paths through space. But those paths also extend through time. And time behaves just as strangely. In the same way that a particle doesn't commit to a single position, it doesn't commit to a single history. The calculation that determines what happens includes contributions from paths that move forward in time, backward in time, and in complicated loops. Again, this does not mean particles literally travel backward in time in the science fiction sense. It means the rules that determine outcomes do not privilege a single narrative of before and after until an interaction pins something down. Cause and effect, like motion, is an emergent concept. At the fundamental level, what exists is a network of constraints linking events, not a story unfolding frame by frame. This is deeply unsettling because it challenges your sense of causality. You want causes to precede effects. You want a clean chain of events. Nature gives you something messier, a global consistency condition that determines which events can occur together. Only after the fact do you sort them into causes and effects. This is why Feynman insisted that trying to visualize what particles really do between measurements often leads you astray. The mathematics works perfectly. The pictures break down. The mistake is not that the theory is incomplete. The mistake is assuming that reality must resemble your intuition. And now we arrive at the most important question of all. If particles don't truly travel through space the way we imagine, and if motion and causality are emergent, then why does space feel so real to us? Why does distance matter? Why does it take time to get from one place to another? The answer lies in constraints. The rules governing how probabilities evolve are not arbitrary. They are tightly constrained by the structure of space and time. Those constraints limit how quickly influences can spread. They enforce what we call the speed of light. They prevent information from appearing out of nowhere. So even though particles don't follow single paths, the effects of their behavior are still local and orderly. Space still matters. Time still matters, but not in the way you thought. Space is not a container. Time is not a river. Particles are not travelers. They are all parts of a single, interlocking system of relationships. And once you see that, you're ready for the final shift in perspective. Because the next thing to realize is this: if motion through space is an emergent pattern, then the universe is not made of things moving around. It is made of processes happening. And that changes everything. If the universe is made of processes rather than things, then space itself starts to look very different. You stop thinking of it as a three-dimensional box filled with objects and start thinking of it as a set of rules that govern how events can relate to one another. An event is something simple. A particle interacts. A detector clicks. Energy is exchanged. Something happens. That's all. And physics, at its deepest level, is not about objects drifting around between events. It is about predicting which events can happen together, and with what likelihood. From this perspective, asking how a particle travels through space is like asking how a melody travels through a song. The melody isn't a thing that moves from note to note. It's a pattern that unfolds. The notes don't carry the melody. The relationships between them do. A particle is like that. It's not a dot moving through space. It's a pattern of correlations between events. Now consider what happens when you try to force the universe back into your intuitive picture. You imagine a particle at a precise location, then later at another precise location. You draw a line between them and call it motion, but that line exists only in your reconstruction. Nature never drew it. What nature gave you were two events, and between those events, the rules tell you how probabilities connect them. The path is not real. The connection is. This is why the equations of physics don't describe trajectories in the way you expect. They describe amplitudes. They describe how likely different events are given other events. The math doesn't care about your mental pictures. It cares about consistency. And when you follow that math honestly, you discover something almost poetic. The universe does not compute the future by pushing objects through space step by step. It evaluates the whole situation at once. Past, present, and future are linked in a single structure. This is especially clear when you look at how particles behave at very small scales and very high energies. The idea of a sharply defined particle becomes less and less useful. Particles can be created and destroyed. They can transform into other particles. They can appear briefly and vanish. So what is it that persists? Not the particle, not the path, but the rules. The rules that determine which interactions are allowed and which are forbidden. The rules that conserve energy and momentum. The rules that enforce symmetries. Those are the real backbone of reality. Space, then, is not something particles move through. It is something that constrains how interactions can occur. Distance is not a measure of how far a particle must travel. It is a measure of how strongly events can influence one another. This becomes clearer when you think about why distant objects affect each other less than nearby ones. It's not because something physically weakens as it travels through space. It's because the structure of space limits how correlations spread. The farther apart two regions are, the fewer ways they can influence each other within a given time. Distance is a bookkeeping device for influence. Time is the same. Time is not something that flows. It is a way of ordering events. When one event can influence another, we say it comes before it. When it cannot, we say they are simultaneous or unrelated. Time emerges from causality, not the other way around. This is why modern physics allows situations where the order of events is not absolute. In some contexts, different observers legitimately disagree about which event happened first. That's not a bug. It's a sign that before and after are not universal facts. What's universal are the relationships. Now let's bring this back to the original question in a more concrete way. When you see a particle travel across a detector screen, what you are really seeing is a series of interactions lighting up in a correlated pattern. Each flash is local. Each interaction happens at a specific place and time. But the pattern they form is not a record of a particle's journey. It is a manifestation of the underlying probabilities. The particle does not carry its identity through space like a tag. What persists is the structure of correlations that links one interaction to the next. This also explains why particles of the same type are truly indistinguishable. Two electrons are not just similar, they are fundamentally the same. There is no hidden label that tells them apart. You cannot meaningfully ask which electron is which after they interact. That question assumes identity is something carried through time. Nature does not support that assumption. Identity, like motion, is emergent. At large scales, where interactions are constant and overwhelming, identities stabilize. Objects acquire histories. You can track them. You can say, "This is the same chair as yesterday," but that stability is not fundamental. It is a consequence of countless interactions locking patterns in place. At small scales, those locks loosen. Identity blurs. Paths dissolve. Now pause and think about what this says about reality as a whole. The universe is not a machine pushing pieces around. It is not a clockwork of objects following predetermined tracks. It is a vast web of relationships, constantly updating, constantly reevaluating what can happen next. Particles are not the actors in this play. They are the grammar. They are the allowed ways the universe can connect one event to another. And when you stop insisting on visualizing particles as little travelers, something remarkable happens. The weirdness starts to make sense. Quantum mechanics stops feeling like a list of paradoxes and starts feeling like a natural language spoken by reality itself. The paradoxes were never in nature. They were in your pictures. Now here's the final twist you need to sit with. If particles don't really move through space, then neither do you. Not fundamentally. What you experience as moving through the world is a sequence of correlated events involving your body, the environment, and your memories. Your sense of continuity is constructed. It is incredibly robust, but it is not primitive. At the deepest level, you are not a thing traveling through space and time. You are a process unfolding within a network of constraints. That doesn't make your experience unreal. It makes it emergent. And emergence is not weakness. It is power. Because from these simple, abstract rules about probabilities and relationships, comes everything you know. Motion, solidity, causality, life, thought. So when you ask how a particle travels through space, the most honest answer is this: it doesn't. What travels is a pattern of possibility. What moves is a structure of influence. What you call motion is the shadow cast by deeper rules. And once you see that, you're no longer just watching particles move. You're watching the universe think. Now that you've followed the idea all the way down, past particles, past paths, past motion itself, you can see why the original question was slightly misframed from the beginning. How does a particle travel through space? Assumes there is a traveler and a road. But at the deepest level, neither exists in the way your intuition expects. Instead, there are only events and the rules that connect them. This is why the universe can be so precise and yet so strange. The precision comes from the rules. The strangeness comes from trying to force those rules into pictures they were never meant to fit. Think about how radical this is. The world you experience, objects moving, causes producing effects, time flowing forward, is not written into the foundations of reality. It emerges when countless interactions lock probabilities into stable patterns. It's real, but it's not fundamental. This is why quantum behavior feels hidden. It doesn't disappear at large scales. It gets buried under overwhelming redundancy. Every interaction you have with the environment collapses possibilities. Every collision, every photon, every vibration pins things down just enough to give you a world that feels solid and predictable. But the deeper rules never stop operating. They are operating in your body right now, in every chemical reaction, in every nerve signal, in every exchange of energy that keeps you alive. You don't notice them because they average out, they cooperate, they stabilize. But if you isolate just one particle, strip away the noise, and watch carefully, the old picture dissolves. This also explains something profound about why physics has such a hard limit on what it can tell you. You can predict probabilities with extraordinary accuracy. You can calculate outcomes to many decimal places. But you cannot demand a story of what really happened in between events. That demand is not something nature agreed to satisfy. Nature gives you rules for outcomes, not narratives. The narrative is something your mind adds afterward. This is why Feynman warned against asking the wrong questions. Not because the questions are stupid, but because they smuggle in assumptions that reality does not honor. When you ask how a particle travels, you're asking for a picture that doesn't exist. What exists is something subtler and more powerful. The universe does not evolve by pushing objects through space. It evolves by updating relationships. Each event constrains the next set of possibilities. The structure tightens, the pattern grows. Seen this way, space is not a place. It is a rule book. Time is not a flow. It is an ordering of influence. Motion is not displacement. It is the reshaping of probability. And particles are not little dots. They are the allowed ways the universe can connect one moment to the next. Once you accept this, many mysteries lose their sting. Particles tunneling through barriers are no longer cheating. They are following rules that don't require paths. Entanglement is no longer spooky. It's just correlation without classical distance. Quantum randomness is not ignorance. It's irreducible openness in how events can unfold. The universe is not uncertain because it's incomplete. It's uncertain because certainty was never part of the foundation. And here's the final thing to let sink in. The fact that the world looks classical to you is not evidence that classical ideas are fundamental. It's evidence that you live in a regime where probabilities are overwhelmingly constrained. You inhabit a corner of reality where patterns are stable enough to feel solid. But solidity is not the ground floor, it's a high-level feature. Underneath, everything is possibility negotiating with constraint. So when you imagine a particle crossing the void between stars, or an electron jumping between atoms, or light traveling from a distant galaxy to your eye, remember this. Nothing is marching through empty space. What's happening is a global consistency unfolding, rules enforcing themselves across relationships, probabilities interfering, histories resolving only when they must. The universe is not a movie reel of moving things. It is a living calculation. And motion is not something particles do. It is something the universe allows. That is why the question of how a particle travels through space doesn't have the answer you expected. Because the deepest answer is this: space is not where things go. It's how things are allowed to happen. And once you see that, you're no longer asking where particles are. You're asking how reality holds together at all. Do you still believe particles actually travel? Or do you see motion differently now? Tell me in the comments. I read every thoughtful response. And if this is the kind of physics that makes you pause instead of scroll, subscribe.